Ever wondered if we could turn our biggest environmental problem into a solution for feeding the world? What if the very carbon dioxide warming our planet could be transformed into the nutrients our crops need to thrive? Welcome to the Fields of Innovation YouTube channel. Smart farming starts here. Discover the future of agriculture, where we share information about technology applied in agriculture. Today, we're diving into a breakthrough technology that sounds like science fiction but is rapidly becoming reality: recycling CO into fertilizer. Number. The global challenge we face is immense. Despite ambitious sustainability goals and climate agreements, atmospheric CO levels continued their relentless climb. Key sectors like industry, power generation, and even agriculture are major contributors. We often think of emissions coming from burning fossil fuels, but the story is more complex. The very production of modern fertilizers, which relies heavily on a natural gas-intensive process, carries a massive carbon footprint. At the same time, the pressure on agriculture is mounting. With the global population projected to reach nearly 10 billion by 2050, the demand for food is skyrocketing. This means we need more fertilizer, not less. This paradoxy need to produce more food while drastically cutting emissions has created a significant technology gap. How can we feed the world without further damaging our climate? This is where CO₂-fertilizer technology enters the scene. It presents a paradigm shift, a solution that doesn't just aim to reduce harmful emissions but actually captures them and transforms them into a valuable, productive resource. This innovative approach is a prime example of a circular carbon solution. Instead of being released into the atmosphere as waste, carbon atoms are captured, repurposed, and integrated back into the agricultural cycle in a way that supports both food production and environmental health. Number. To understand how a greenhouse gas can become plant food, we first need to look at how we capture CO in the first place. This is the critical first step in the process, and scientists are pursuing two primary methods. The first is direct air capture, or DAC. This involves large-scale machines that act like giant vacuums, pulling CO directly from the ambient air. While technologically remarkable, this method is extremely energy-intensive. CO in the atmosphere is very diluted, making up only about 0.04% of the air, so filtering it out requires a tremendous amount of power. The second, more common method is point source capture. This approach is far more efficient because it targets CO at its source, such as the smokestacks of cement factories, ethanol plants, or power generation facilities. Here, the CO is much more concentrated, sometimes making up 10% or more of the exhaust stream. Capturing it before it dissipates into the atmosphere is significantly cheaper and requires less energy, making it a more economically viable starting point for carbon recycling. Once the CO is captured, it isn't pure enough to be used immediately. It must be separated from other gases and purified. Several advanced technologies make this possible. Amine-based sorbents are chemical solutions that act like sponges, selectively binding with CO molecules and then releasing them when heated. Membrane technologies work like highly specialized filters, allowing CO2 pass through while blocking other gases based on molecular size and permeability. Another fascinating method is mineralization, where CO is reacted with minerals rich in magnesium or calcium to form solid, stable carbonates, effectively locking the carbon away in a rock-like form. Despite these innovations, significant engineering challenges remain. The energy consumption and high operational costs associated with both capture and purification are major hurdles that currently limit widespread adoption. Overcoming these barriers is key to unlocking the full potential of CO as a resource. Number. This is where the real magic happens, turning captured carbon dioxide into a nutrient-rich fertilizer. Scientists and engineers are developing three major pathways to achieve this transformation. The first is electrochemical conversion. This cutting-edge method uses electricity, ideally from renewable sources like solar or wind, to drive chemical reactions. In a specialized reactor, captured CO is combined with nitrogen from the air to create urea, which is one of the most widely used nitrogen fertilizers in the world. This process offers several advantages. It can operate at ambient temperatures and pressures, unlike the traditional energy-intensive methods. It's also highly scalable and modular, meaning small-scale reactors could one day be installed directly on farms, producing fertilizer on-site and on. In these systems, catalysts and electrolytes facilitate the rearrangement of CO and nitrogen molecules, creating new, nitrogen-rich compounds that plants can absorb as nutrients. The second pathway is biological conversion. This method harnesses the power of nature, using specially engineered microbes or algae to do the heavy lifting. These microorganisms can absorb CO through processes similar to photosynthesis or nitrogen fixation. They are optimized in a lab to efficiently convert the carbon and nitrogen they consume into forms that are valuable for agriculture, such as ammonium, nitrates, or other bio-based nutrient sources. A key benefit of this approach is its low energy requirement. as these biological systems often operate at low temperatures and pressures, making them a potentially more sustainable option. Finally, there is the mineralization pathway. As mentioned earlier, this process involves reacting CO with alkaline minerals to produce stable carbonates. While not a traditional fertilizer in the sense of providing primary nutrients like nitrogen, these carbonates act as powerful soil amendments. They can improve soil structure, enhance water retention, and help balance soil pH levels. By improving the overall health of the soil, these mineralized products create a better growing environment for crops and offer long-term climate benefits by sequestering carbon in a solid, stable form. Each of these pathways offers a unique way to take a waste product and turn it into a cornerstone of sustainable agriculture. This groundbreaking technology isn't just confined to laboratories. It's being tested and deployed in the real world. In the United States, a vibrant ecosystem of startups is pioneering these solutions. Some companies are focusing on producing electrochemically derived urea, while others are developing carbonate-based fertilizers. Many are forming strategic partnerships with ethanol plants, which provide a cheap and concentrated source of CO. Early field trials are showing promising results, with reports of improved crop yields and a significantly reduced carbon footprint compared to conventional fertilizers. In Canada, the focus is heavily on mineralization. Companies are leveraging the country's abundant mineral deposits to create CO-enhanced soil additives. Canadian researchers are at the forefront of testing the durability and stability of these carbonate products, especially in colder climates, ensuring the captured carbon remains locked away for the long term. Across the Atlantic, the United Kingdom is piloting highly integrated carbon recycling systems. These ambitious projects combine renewable energy sources, advanced vertical farms, and CO₂-derived fertilizers to create self-sustaining low-emission agricultural hubs. The goal is to build a circular economy within agriculture, where waste from one process becomes the input for another. Meanwhile, in Australia, researchers are tackling the challenges of dryland farming. Trials are focused on how mineralized fertilizers can improve soil conditions and water retention in arid and semi-arid regions. Australian companies are also making strides in microalgae-based systems, using sunlight and CO₂ to cultivate nutrient-rich biomass that can be used as a biofertilizer. These real-world applications, backed by performance data on yield, soil health, and carbon reduction, are demonstrating the tangible impact of this transformative technology. Beyond the environmental benefits, strong economic incentives are driving the development of CO₂ fertilizer technology. One of the biggest motivations is reducing the agricultural sector's dependence on natural gas. The conventional method for producing nitrogen fertilizer, known as the Haber-Bosch process, is incredibly energy-intensive and consumes vast quantities of natural gas. This leaves farmers and entire nations vulnerable to volatile and often unpredictable price spikes in the global energy market. By contrast, CO-based fertilizers promise greater price stability over the long term. Their production relies on CO, which is an abundant waste product, and electricity, which can be sourced from renewables with increasingly stable and predictable costs. For countries like the US and UK, which have recently experienced sharp increases in fertilizer prices that have squeezed farmers' margins, this stability is a powerful economic driver. Currently, the cost per ton of CO₂-derived fertilizer is still higher than its conventional counterpart. However, this is changing rapidly. As the technology scales up and production becomes more efficient, costs are expected to fall dramatically. Furthermore, when you factor in the value of carbon credits, government tax incentives for sustainable practices, and the long-term economic benefits of improved soil health, the financial argument for carbon recycling becomes increasingly compelling. This is why governments and private investors are pouring significant capital into these technologies, recognizing their potential to create a more resilient and profitable agricultural economy. The environmental and climate advantages of this technology are perhaps its most compelling selling point. The most obvious benefit is the creation of a lower carbon fertilizer. By capturing CO and converting it into a product, the technology transforms a pollutant into a valuable resource. The fertilizer itself essentially carries embedded carbon savings, representing greenhouse gases that were prevented from entering the atmosphere. This fundamentally changes the carbon footprint of farming. Beyond carbon reduction, these new fertilizers offer other important environmental benefits. Some CO₂-derived fertilizers have a lower acidifying effect on the soil compared to conventional nitrogen fertilizers like ammonium nitrate. Over time, soil acidification can degrade soil health and reduce crop productivity, so this is a significant advantage for long-term land stewardship. Additionally, certain CO-based fertilizer formulations are designed for slow and controlled nutrient release. This means that plants can absorb the nutrients more effectively over a longer period, reducing the risk of nitrogen runoff into nearby rivers and streams. Nitrogen pollution from agricultural runoff is a major environmental issue, leading to harmful algal blooms and creating dead zones in aquatic ecosystems. By improving nutrient use efficiency, this technology not only supports climate goals but also helps protect our vital water resources and promote healthier soils. Despite its immense promise, the path to mainstream adoption for CO₂ fertilizer technology is not without its obstacles. A realistic assessment reveals several key challenges that must be addressed. First and foremost is energy intensity. Some of the most promising conversion systems, particularly direct air capture and electrochemical reactors, require a substantial amount of electricity to operate. For this technology to be truly sustainable, that power must come from renewable sources. The scalability of these systems may therefore be limited by the availability of affordable, abundant green energy. Another significant hurdle is the complex and often slow process of regulatory approval. Fertilizer regulations differ widely across the US, UK, Canada, and Australia. New products must undergo rigorous testing to ensure they are safe for the environment and effective for crop growth. Gaining certification can be a multi-year process, creating a bottleneck for companies eager to bring their innovations to market. Finally, there is the crucial challenge of farmer adoption. Farmers are business owners who operate on tight margins and are understandably cautious about adopting unproven technologies. They will need to see extensive, long-term field trial data that guarantees performance, yield benefits, and a clear return on investment. Until CO₂-derived fertilizers can compete with conventional products on both price and reliability, widespread adoption will remain a significant barrier. Looking ahead, the potential for this technology to reshape agriculture is truly profound. The long-term vision is the creation of net-zero farms, where energy, emissions, and nutrients operate in a closed, circular loop. Imagine a farm where CO captured from its own operations or the local community is used to produce the very fertilizer it needs to grow its crops, all powered by on-site renewable energy. This integration with renewable energy is a cornerstone of the future vision. Solar and wind-powered electrochemical reactors could enable decentralized, local production of fertilizer. This would not only eliminate the emissions associated with the long and complex global supply chain but also give farmers greater control over their nutrient supply. Experts project rapid growth in this sector between 2030 and 2040. As technology matures and economies of scale bring costs down, the fertilizer market is expected to shift away from large, centralized production plants and toward a more distributed network of on-site CO processing systems. If scaled globally, CO₂ fertilizer systems have the potential to massively reduce agriculture's overall emissions while simultaneously strengthening global food security. It represents a fundamental transformation in how we think about waste, resources, and the very foundation of our food system. In conclusion, recycling CO into fertilizer is more than just a fascinating scientific breakthrough. It represents one of the most impactful and promising agricultural innovations of the 21st century. It tackles two of our greatest challenges: climate change and food security, with a single, elegant solution that turns a liability into an asset. We'd love to hear your thoughts on this technology. Do you think this is the future of farming? Leave your questions and insights in the comments below. If you found this video informative, don't forget to subscribe to Fields of Innovation for more episodes on the cutting edge of agri-tech, and let us know if there are other topics you'd like us to cover in the future.